Part C, an equals e to the n over n. Does it converge? As n gets bigger, does it converge to anything? What's your gut tell you? How does e to the n compare to the denominator n? A lot bigger, right? It gets a lot bigger eventually, right? So what's your gut tell you? It's going to diverge to infinity, yeah. How do you prove it? That's the rule you'd like to use if you can. Problem is, L'Hopital's rule involves taking derivatives of the numerator and denominator, right? How do you take the derivative of e to the n? When you graph it, it's just a bunch of dots. It's not a continuous function. How do you take the derivative of n? It's just a bunch of dots. It doesn't really have a slope associated with it. I suppose it does, but not in the derivative sense. Well, it's okay then to do this. You can look at the related function. The related continuous function, FCTN for short, is f of x equals e to the x over x. And I haven't proved it, but this at least seems intuitive. The limit as n goes to infinity of an, this is for any an, should equal the limit as n goes to infinity of the related function. For limits at infinity, there's no reason why they wouldn't do the same thing. They'd either both converge to a number or they'd both diverge to infinity, perhaps. If you have negatives in there, they could go to negative infinity. Or maybe certain functions could oscillate between two numbers. But they should do the same thing. And so we're going to use that fact to help us use L'Hopital's rule. So what we'll do is we'll consider the related function f of x equals e to the x over x. And let's look at that, the limit as x goes to infinity. Should have been x right there. The limit as x goes to infinity of e to the x over x. Well, okay, before I put in an equals, if you're going to use L'Hopital's rule, what form does e to the x over x have to take on? Either infinity over infinity, plus or minus, or 0 over 0. Pretty clear, I hope, that it takes on the form infinity over infinity. So big old check mark, L'Hopital's rule applies. Okay, so then by L'Hopital's rule, h, this limit should equal the limit as x goes to infinity of, what's the derivative of the top? Derivative of e to the x is e to the x. What's the derivative of x with respect to x? 1. Now can you take the limit? Yeah, you know what e to the x does as x goes to infinity. It goes to infinity. So you could say that an, which is this guy, if you want to use the shorthand notation, you could say that guy also diverges to infinity. As goes the related function, so goes the sequence, in other words. But that's how you do it. And students hate that. They hate changing to x, but that's the proper way to do it. So we'll skip to part E. an equals tangent inverse n divided by n plus 1. Be nice to compare this guy to one or two simpler functions whose limits are known. And the good news is you can do that. What's the tangent inverse of n less than? It's less than pi over 2. So you could say this, since tangent inverse of n, since we're not allowed to plug in anything smaller than 0, it's actually bigger than or equal to 0. And if we only let n start at 1, it's going to be strictly greater than 0. And less than, it won't ever get to pi over 2. The less than strictly pi halves. So since that's true, comma, we could say that the tangent inverse of n over n plus 1, do I have to use pi over 2? So I want to say it's less than something over n plus 1. I could use pi over 2 here, but what's an easier number to use? Pi over 2 is about 1.5, right? So couldn't I just use 2 instead? I'd still be safe, right? It's still true. So I could say this. Tangent inverse of n, and again, I switched from or equal to strict inequality, but it will be true. Tangent inverse of n, since n's a whole number, it'll always be bigger than 0, since it's actually a counting number, n is. So does everybody agree with that inequality? So where am I going with this? What's the limit of the right-hand side as n goes to infinity? 2 over n plus 1. Denominator increases without bound. Numerator stays the same. 0. What's the limit of the left? That's the limit of the right-hand side. What's the limit of the left-hand side? 0. The limit of 0 as n goes to infinity is 0. So what's the limit of the function squeezed in between? 0. Okay. So you could also say now the limit as n goes to infinity of 0 equals 0, which equals the limit as n goes to infinity of 2 over n plus 1. So notice all in one statement, I took the limit of the left and the right sides of that inequality statement. And then if you like, you could say thus, therefore, behold, or just so. So the an we're interested in, tan inverse over n plus 1, converges to 0. Oops, I mixed notation in there for you. So I use limit up here and arrow notation down here. If you know how to use notation, that's fine. But if you're not comfortable with the different forms of notation, use the LIM notation, okay? If you're not sure how to write it correctly, stick with one notation, and the LIM notation works every time. So stick with the longer notation if you're not sure. So the limit of the tangent inverse of n is over n plus 1 is equal to 0, or you could say tangent inverse of n over n plus 1 converges to 0. Either notation's fine. By what theorem? By squeeze theorem. Whoops, got to spell it right. By the squeeze theorem, or just squeeze theorem. Notice the parts of this proof. The devil's in the details here, you guys. You've got to be able to come up with like this inequality here. An inequality that you know what the limit of the left-hand function is. You know what the limit of the right-hand function is. You know it. So in your mind, the proof is already done at this point. You already know where you're going, right? And then you do have to make a statement about the values at the end. So the limit values for the end functions left and right. And then you make a conclusion. It is much like the comparison theorem that you're going to do today on the test.